Hello and welcome back to Intelligence Dive. Today is going to be the first episode of a brand new series named Deep Dive. Instead of having a regular podcast episode where two or more people discuss various topics, Deep Dive is an avenue for scholars and members of academia to share their passion for a subject by breaking it down in the form of a solo video essay. With that said, if anyone is interested in having their own episode, please message me on my Twitter profile that you can find a link to in the description below. So here is today's episode.
Hello, my name's Ben Alexander, and in this first episode of Deep Dive, I'm going to be talking about quantum computing and all of the different uses, how it's come about, why we need quantum computing. But first, I think we should define what classical computing is, which is essentially using transistors like you have in a laptop or in a phone. And the way this works is it uses binary machine code, which is essentially ones and zeros, either electricity being on or electricity being off. And these have numerous other things such as RAM, your storage, your input output, the user interface. However, I think we should also dive even deeper into how we got there in the first place, so then we can understand how we can move into the future with quantum computing. So, classical computing essentially started with World War II. Classical computing with World War II, when the wars drove innovation due to trying to crack the Enigma in World War II. And this was done with the Colossus. And currently that's held in Bletchley Park and was also cracked in Bletchley Park. And it's the National Museum for Computer Science. I recommend you go if you have an interest. I've been myself, and it's amazing how physically big these machines are, it being the size of a room, with the valves, which is what used to be transistors, being like that big, like the size of your hand. Now they're nanometers big. And they would essentially take in punch sheets up to 5 bits. It would get scanned, converted into the memory, and then the thermionic valves would either represent the one or the zero by having them constantly heated. And then if you'd increase the power, that would allow electrons to flow through the vacuum, which would give you your one signal. If not, then a zero. However, we found that essentially every 10, 15 minutes, one of the thousands of valves would go, which would then mean the whole system's redundant until you find that fix. And as you'll see in quantum computing, that's quite similar to what we've got right now. It's quite unreliable. But going back to transistors themselves, the current issue we have is that we can't get any better than what we have right now. We have up to 5 nanometer architecture, which means that the gap between each transistor is 5 nanometers, which gets to the point where electrons are able to exist in two transistors if we go any closer, meaning that quantum physics itself is preventing our expansion with current transistor technology. And up until this point, there was something called Moore's law, which is where the transistors would either half in size or double in power every 2 years. However, we've seen that slowly slowing down over time because we can't get any closer. So this is where quantum computing actually comes in. And to understand quantum computing, I'll give a brief rundown of how quantum physics itself works. So any quantum particle has something called superposition. And a good way to explain this is the classic Schrodinger's cat, which is where if you put a cat in a box and you give it poison, which has 50% chance of it killing the cat and 50% of it surviving, you put it in the box, you close the box. Until you open the box, you don't know if the cat will be dead or alive. So you could say that whilst the box is closed, the cat is both dead and alive at the same time, which is superposition. The cat exists in multiple states. It's dead and alive. However, it only chooses whether it's dead or alive under a external impact. So someone viewing or light being shone into it, just anything that interrupts it will then make it choose a position. And this is essentially how quantum computing works. It uses superposition to be able to process multiple things at the same time, essentially making it millions of times faster than current computing. And quantum computers itself, there are two main ways that we can do this, either with a metallic superconductor or with trapped ions. And in both cases, they have to be essentially less than a degree above 0 Kelvin, which is like the coldest it can possibly be. So minus 273 degrees Celsius. And it has to have nothing interacting with it. So no light, no particles bumping into it. It can't have any even quantum vibrations. Otherwise, it loses its quantum state and chooses one of the options, which defeats the point. And so metallic superconductors in its quantum state allows electrons to both flow clockwise around it. Imagine it as a ring, a clockwise around it, or anti-clockwise, or both at the same time, which is the quantum effect of superposition. Or we can use trapped ions, where essentially a metal ion is trapped inside a magnetic field where it's essentially levitated inside a vacuum where no other atoms can hit it. There is no radiation that can get in. And then you essentially line up these ions into a line, and that essentially is like putting a transistor next to another transistor, which increases the power. And currently we've got up to 14 ions next to each other. So these are all called qubits, so 14 qubits next to each other. Which was done by Rainer Blatt's group at the University of Innsbruck in Austria. And the issue with this, however, is that when the particle is viewed, then it chooses one of the possible outcomes. So all of that quantum stuff that we've been trying to do to avoid this is gone. And another problem is that it only gives a percentage of the correct answer. So say it's 70% this or 30% that, then you've got to choose which one. And going back again into the origins of computing, it was initially done by Richard Feynman in a conference, and he essentially asked that, can we use quantum physics to simulate quantum physics? Because currently using classical physics to try and emulate quantum physics, it doesn't work because, as I'll get onto later, we don't have the power of that in classical computing due to the amount of combinations. And this was in 1981. And then an American mathematician named Peter Shor at Bell Labs then founded the first theoretical way to use computers to break encryption. And his program was able to crack an encrypted message in hours compared to billions of years. And we'll go on to the issue of that as well. However, looking at the power theoretically of quantum computing, if we had a sequence of 30 bits, it would have a billion possible values. This is for either quantum computing and classical computing. However, with classical, it could only be one of those billion states at a time. You can't have it existing in multiple states because that's superposition, that's quantum physics. And if this was a quantum machine, then it would be able to exist in those 1 billion states at the same time, meaning that if we wanted to emulate that using classical computing, we'd have to have a billion different processors running at the same time. But only one quantum processor is needed to do this. So that's where the power comes in, of being able to run so many things at the same time. However, currently the supercomputers can be off by 70% to 100% on simple molecules like caffeine. This is with classical computing. And this is due to even a small molecule like caffeine being so small, only a few tens of different atoms interacting. We don't have that power currently. However, quantum computers can get exponentially more powerful for every qubit that's added, which essentially keeps up with nature's exponential probabilities. Because classical computing, if you increase the amount of transistors, your power goes like that. However, nature goes like that. But quantum computing can keep up with that curve, meaning that in theory, you could begin to emulate things that are massive. For example, say 300 qubits of data was representing a number register, we'd be able to hold more possible numbers than there are atoms in the known universe. And even with only 100 qubits, a quantum computer would have more processing power than all of the supercomputers in the world combined. So that just shows part of the power of quantum computing and why it's even being researched in the first place. However, if we then dive into the uses, quantum physics is using physics to describe physics. So we'd be able to use quantum computers to simulate quantum physics. And this is because if we use classical computing, we'd have to be able to account for electrons and particles having in total millions of possible different states. For example, in an electron, 4 electrons have 16 states. That's manageable easily. 10 electrons, 124 states, again, quite easy. 20 electrons, a billion states. That's still doable. You'd be able to essentially model one tick of the system every second. If a process is able to go through a billion different instructions, then this is still doable. A laptop would be able to simulate 26. However, a supercomputer, just to double that, wouldn't be able to do it. If you want to double the amount of electrons, a supercomputer can only do up to 43 electrons. And that means that we don't essentially have enough power to simulate this area of physics. So what quantum computing can do, it can essentially simulate the areas of physics that we can't replicate normally. For example, you can do a physics experiment to test gravity, but you can't do it to test how particles react at like a percentage away from the max energy they can have. So it can be used for high energy physics, what actually happens in chemical reactions, the way electrons interact with each other, and things like astrophysics with large masses. And that's the first way that we can use it for simulations of physics. However, we can also use it in the data science world. For example, if there is a phone book of a million numbers and we just have to find the number, it would take, if we're using a linear search, although there are other different searches, it would take on average 1 million iterations for a classical computer to find it. However, a quantum computer would only take 1,000, which is a massive step up. So therefore, it's really good for those needle in a haystack cases where you need to find something very small in massive data, meaning that for data science, quantum computing will be able to increase the speed and increase the efficiency at where we can find data. And on the topic of needle for haystack cases, the way encryption works. So encryption itself is used to essentially make sure that if someone finds your data online, they won't be able to read it. So it's like scrambling the data before you send it, and at the receiving end, they're able to unscramble it. And the way this works is it uses something called a key, where this key is essentially the code which scrambles it. So you have a key to scramble it, and then that same key can be reversed and you unscramble it. However, this is done through prime numbers. So essentially you get 2 primes, which are 64 or 32 numbers long, massive primes. You multiply them together to give you one big prime. And the way this big prime is then your key. And the way currently we'd have to go about cracking this encryption key would be to find every single large prime number which multiplies to this key. However, when this number is, hundreds of characters long, it becomes nearly impossible. To the point where it takes billions of years for classical computers. However, believe it or not, a quantum computer will be able to do that in a matter of hours. So all of the bank transfers, all of the money transfers, any sensitive files being sent, a quantum computer catches it, it will be able to unscramble it. Now, this isn't an issue yet, since quantum computers are barely a thing right now. They're more theoretical in the process of being developed. They're only in the biggest universities. It's not something common like a laptop or a phone, so you don't have to worry about that yet. However, that just goes to show the power that it does have. The governments can harness this power, if big companies can harness this power. So that just goes to show why we're developing quantum computing in the first place. The processing power it has is unbelievable. And as we can see in today's age, the more power we have, the more we can use it. We've gone from computers being essentially calculators, and the Apollo space mission to the moon had a computer as powerful as a modern day calculator. But now look at how, if we use our devices, we can play games graphically, we can have AI, we can have data science, and the more power we have, the more experimentation we can do in the world of computer science, which leads to innovation, which leads to better for the consumer. So looking into the future, IBM by 2023 are attempting to have a 1,000 qubit computer, which I think is being a bit ambitious, seeing as currently they don't have much to show for that. However, Google, they believe they'll have a quantum computer fully working by 2029, and similar to Facebook's OpenAI, they'll make this as a cloud infrastructure so people can use this system without having to actually go there. They're able to write the quantum code and then have Google run it for them. And they opened a quantum computing AI campus in Santa Barbara County University, which used the electric current in superconducting rings, as I explained earlier. And with 1 or 2 qubits, they can have an accuracy of 99.4 or 99.2%, which is quite impressive considering that these supercomputers only work for fractions of seconds. So if we can bring down the error and we can keep them running for longer, then the power they'll have will just increase exponentially. Because currently we're working with larger errors and also them barely working for splits of seconds. However, if we can find new ways to, different things to put into into quantum states, then we can essentially have a boom like the transistor was. And who knows what the future has to offer. I personally don't believe that they'll be in things like phones, considering they need to have 0 interruptions. They're incredibly fussy on their conditions. It has to be a complete vacuum. It has to be essentially 0 Kelvin. You can't be walking around with something that's minus 270 degrees inside your phone. These things cost billions and take up buildings to essentially keep it cool enough. So I believe this will be more of a cloud infrastructure where you'll have main quantum computers and then you can access them. However, I don't think they'll be in phone technology. So that essentially wraps up everything that I've researched on quantum computing. I personally find it fascinating, and the different possibilities we'll have with them and how we've even made this technology in the first place is something that's amazed me. And yeah, that's the first episode. I hope you've enjoyed, and I'll see you guys later.